Welcome everybody to this 3.5 hour tour de force of computational MIP solving. Am I a bit too loud? Yeah. So let's look at computational MIP. As Bob Bixby, as I would say, the godfather of computational MIP, put it once, MIP solvers are a bag full of tricks. And we have already on Monday heard from Martin some other very impressive numbers about the power of MIP solving, also given by Bob, that in the last 32 years, hardware got about 1 million times faster. And at the same time, the MIP software, the MIP algorithms evolved from what they were back then, still or already branch and bound with some of the tricks that we will show today were already in there at that point. But over those 32 years, researchers have put numerous more subroutines, developments, algorithms, ideas, new research results into these solvers that made them about 6 million times faster. And yeah, since these are completely orthogonal developments, you can essentially just multiply them together and get an impressive speed up. On top of that, CPU speedups in a certain sense have faded out over the past decade already. Definitely when it comes to single cycle or single thread speedup, we've just hit physical limits at this point. CPUs go more and more parallel, but definitely not at the speed they did previously. And of course, there's new hardware coming up. I won't cover this today at all, but the MIP solver development is still going strong. There's also kind of an effect of diminishing returns on individual contributions, but Express and the other commercial solvers in the field still show 2-digit speedups per year. You know about exponential growth, so this quickly multiplies up. So today, let's take a look into the back. What is inside these solvers? The first thing that you see when you look inside the back is something like this flowchart, a simplistic flowchart of a MIP solver with the different routines that we are going to cover today. You start with some pre-solving, some massaging of your problem before you go into the actual solving process. And then what you see here is essentially the loop of a branch and bound algorithm. You select some problem to solve. Afterwards, you split it in to 2 or more new problems and then go in a cycle here. And in between, there are these extra procedures like cutting plane generation, heuristics, domain propagation, conflict analysis. Maybe I should say in the beginning with what domain propagation means, because I will be using the term a couple of times and might not be familiar to everyone. This is something like a local, reduced, fast version of pre-solving. You look at the local bounds of your variable that you modified due to your branching procedure and try to deduce other variable bounds from that by logic implication. That's what domain propagation means, and that's good enough for the rest of today to understand when we will be using that term. In the first lecture, we will be looking into the branch and bound algorithm, the core of the MIP solver, if you wish, and talk about different aspects of the branch and bound algorithm. We're gonna give a very quick introduction, then we look at 2 different branching rules, and in the end, we will briefly cover node selection. Okay, so let's get a refresher. What is branch and bound? A method that has been around for many years. This is the original paper where branch and bound was introduced. One thing that I find fascinating is that this procedure, which at least to me seems so intuitive, that's the first thing I would think about how to solve a complex problem, try to split it up and essentially enumerate it. This has been introduced after the cutting plane procedure. So the first thing people came up with was the cutting plane algorithm. And only a couple of years later, branch and bound was formally introduced and presented by these two women, Alison Doig and Alicia Land, who, as I learned recently, met for the first time at the very first IFORS conference, the International Meeting of Operations Research Societies. And to make it LP-based branch and bound, the inventor of the simplex algorithm, George Danzig, was also there. So what a crowd. And this is Alison Harcourt, who was born with the surname of Doig, who has still been teaching until her late 80s at the University of Melbourne, received an award by the Australian government for that. I had the pleasure to meet her some 15 years ago. This was one of the situations. I was giving a presentation at the University of Melbourne about some new branching rules, and before I started, someone came to me and said, "Does that you know, the inventor of branch and mount is in the room today." I was very grateful for this. So what did these two ladies come up with some 70 years ago? LP-based branch and bound, the colorful picture. Short disclaimer for today, all my pictures will be 2 or 3 dimensional because my 10-dimensional drawing skills are still evolving. But always keep in mind, we are looking at the toyest of toy examples. In practice, all these methods will be applied to way bigger problems. Okay, so the branch and bound algorithm, well, starts with selecting a problem to solve first. In the beginning, this will just be the original problem. You solve the linear relaxation of it. This gives you a point that you branch on. You take one of the fractional variables. So you have a choice here. There's 2 variables that are fractional. You split the domain of the variable along one of the variables and create 2 subproblems. By that, that's the branching step. Then next, you select one of your subproblems. That's the selection, node selection step. Node because you are representing your procedure as a tree. Solve the relaxation. Same thing again. You pick one of the 1 fractional variables. Select the new problem, solve the relaxation. Now you find an integer feasible solution. That's great. So for the remainder of the search process, you can ignore everything that has a worse objective. So your bounding can be applied with respect to the objective of this solution. You select a new problem. This is now the empty problem up here that we branched before. Infinite relaxation value, so we definitely can prune this node here, and so on and so forth. At some point, we'll find the optimal solution, have to do some cleanup work in our tree here, and are done solving this. You saw that in this simple algorithm, there's 2 main points where you make a choice. First of all, which variable do you branch on? And second of all, which is the subproblem that you select next? While they might seem equivalent at first glance, one of them is way more important than the other. So the node selection essentially decides the order in which you traverse your search space. There's considerations among that, but it's by far not as important as the decision how you build up your search spec. How do you split it, which is the variable selection step, which is why most of the research and also most of the presentation today will focus on this part here. The main goal in variable selection, at least for now, is try to improve the dual bound. So proving optimality in general is harder than finding a good or an optimal solution. So this is the main focus of this part of the algorithm. You can easily think of some example where a bad selection in the beginning would essentially just duplicate your search space. If you branch on something which has no effect on the optimality proof whatsoever, you just gonna double your search space, do that a couple of times, exponential explosion for no good. So we need to do something clever here. And that is the question, what is a good rule for branching? And And you might say, well, okay, that's something that I already learned. In my textbooks, in the OR classes that I took, it says I branch on the most fractional variable. That's the most undecided variable. That should be good for something. So lift your arm. Who has heard this in a class, in a textbook? Most fractional branching seems to be a thing, right? Well, no. Of course, for theory, that's perfectly fine, and it's the easiest thing to explain in a book, but it's terrible in practice. It's as bad as just branching at random, and that's not very good, as you might imagine. There's a couple of reasons for that. Mostly it's about doing degeneracy, and you really can do, on average, not only in some specific cases, orders of magnitude better than this. So let's look how. And the most important ingredients here are strong branching and pseudo-costs. So let's start again with something like a brute force method. Strong branching. Keep in mind the goal is to improve the dual bound. How can you ensure that this happens? Well, you just compute it beforehand and then select the best option. So in strong branching, for all your branching candidates, again, here this would be 2 because this is slightly off integer. You would create 2 possible, or the 2 subproblems for each of the fractional variables. Solve each of the APs. You see this getting expensive already. And then select the best one, the one that improves the dual bound the most. Okay, so that's very effective with respect to the number of nodes. It's essentially the best branching rule if you just want to reduce the computational complexity of the search. But it's expensive with respect to time. You have to solve a lot of linear programs. That's not particularly cheap. There are some side benefits that you get when doing strong branching that I would like to point out. So if one of these sides is infeasible, you can already use this deduction. You don't need to do that branching, but you can apply the bound change at the node where you were starting from. Then, if both sides are infeasible, of one of your branching candidates, doesn't matter what, you prove that the remaining subproblem as a whole is infeasible. You can prune the node at this point. And as a side effect, you might find feasible solutions. It just, all of this happens in the branching bound algorithm anyway. You just do it like 1 step earlier by your look ahead. And there's numerous ways how you can speed up strong branching. You can only apply it for some of the candidates, potentially when you don't see an improvement for some time. The one that you have might not be optimal, but decent enough. You can limit the number of simplex iterations, so don't solve these strong branching APs to optimality. A very special case here is doing a single simplex iteration. If you dive into the details of the simplex together with Julian, he will be able to explain you why a single iteration is so much faster than doing 2 or more iterations, because you don't need to explicitly perform this. You can just do a ratio test and compute the change directly. So these are so-called Ribak penalties, and they still play a role as a sub-procedure in branching rules today. Okay, there's domain propagation. Another somewhat recent improvement and extensions suggested by people here at Zip is to integrate the domain propagation procedures into strong branching. So before solving your strong branching APs, you propagate the bound changes, the single bound change that you did in branching. Like here for this example, you might get an additional deduction here and thereby get a different, better AP value, also better estimating what will actually happen at that node once you get to solving it. Again, an important special case of this is branching by probing, which would mean that you only apply the domain propagation procedure. You don't solve the AP afterwards. You just propagate bounds and then do some deductions from there. If you're really lucky, you also get a deduction or get an improvement of the dual bound, but at least you can analyze how many other bound changes this branching triggered. Okay, let's come back to how to try to improve the dual bound. I described the drawbacks of strong branching, namely the expensive computation. And strong branching has been suggested in the 90s. I think way earlier, people came up with the idea of pseudo-costs, where strong branching is an explicit a priori observation. Pseudo-costs are something that are computed after you did the branching, and you will then remember that information and use it for future decisions. Yeah, an estimate of the objective gains based on past branching observations. You just observe what happened the last, whatever, 10, 20, 100 times you branched on a certain variable and try to predict the future from that. So for this, you compute the objective gain per unit fractionality. So you have the fractionality. Always this goes in both directions. So there's one value for branching down, one for branching up. Then you, when you update your pseudo-costs, we are in the update step here. So you already branched. And now you want to learn what did that branching do to you. So in the situation where you had branched on that variable, solve the LP inside your branch and bound tree, observed a certain objective improvement. You can assign to the variable that you branched on, okay, the last time I performed this branching, I observed this objective change scaled by the fractionality. You can do the same thing for the upwards branch. This will be asynchronous. Of course, you might visit one of the siblings much later than the other. And then you can take your pseudo-costs or compute your pseudo-costs as just the average of all those observations that you made so far. The picture here illustrates essentially what you do is if on the y-axis you consider the objective value, is that you compute the tangent of this angle here, and larger is better, is more change. Okay, now assume you have some past observations, you have your pseudo-cost initialized, then you can use them to estimate the increase of a future branching that you're about to do. So you apply your pseudo-cost essentially by computing this angle here. You know your fractionality at the LP where you currently sit and want to take a decision. And for all branching candidates, you see, okay, in the past, I had something like this slope on after a branching, and then do your predictions. That's a simple multiplication. So that's as fast as something can get. So it's an algorithm that's at the core of the most state-of-the-art branching schemes. It's very cheap to compute, as I just said. It gets better and better during the search, but there's a couple of cons here. Well, the values might show a large variance. It attributes all of the changes to the last branching, where the objective change might rather be triggered by a sequence of branching that you saw before. This is kind of an open question on how you could improve this behavior. And people, therefore, and the most important drawback is that in the very beginning of the branch and bound search, this is when you make the most crucial decisions. The very first branching is the most important one, full stop. If you mess this up, double search effort. That's the point where I don't have any pseudo-costs available. Pseudo-costs get better towards the end of the search. So you need to do something. Standard idea, well, the first time when you see a variable being fractional, you strong branch on it. Afterwards, you have your pseudo-costs initialized, and then use pseudo-costs from there on. Even better, suggested some 20 years ago, is to have a reliability threshold. So the first 4 to 8 times you see a variable fraction and you do strong branching, and then you consider your pseudo-costs trustworthy. More recently, people looked into making this k not a fixed parameter, but depending on the variance of the pseudo-cost value. Just intuitively, if you look at this here, where would you say that the average is a better representative of what happens in these values here? Most likely the upper one, even so this is less points less observations that you made. And yeah, some more open questions around pseudo-cost and strong branching. Should a strong branching that hit the iteration limit be considered reliable or not? I would like to know a good answer to this. And should we reconsider strong branching when some subproblems behaves differently? That's very vaguely formulated. But like assume you always observe the same thing when doing a strong branch or a pseudo-cost branch. Like for example, you never saw an objective change, and then suddenly after you start branching, you do start to observe that now the behavior changes. Would that be a good point to throw some more strong branching into the game? Okay, so let's quickly double check what we learned so far. A short quiz. I would kindly ask you to just read through this for yourself. Try to maybe take a note of the answers that you think, or take a mental note, and I'll be quiet for 30 seconds or so. Okay, let's check. Question number 1, pseudo-costs are, and what's the answer that you have, A, B, or C? Exactly. So they are a heuristic estimate of the objective change when branching, neither an under nor an over estimator. They are heuristic. Then question number 2, strong branching. When is it very competitive, very effective, for which measure? Yeah, great. So it's very competitive with respect to the number of nodes, not so much for the other ones. And then the final question, a main drawback of pseudo-costs are. Yay. So they are all uninitialized when the most important branching are taken. Cool, you get the main takeaway messages. That's great, so all good now. Well, but what if pseudo-costs don't work? Sorry, I have to be pessimistic here. There are a couple of situations when pseudo-costs might not work well. So what if your problem doesn't have an objective? I was all the time talking about you want to improve your objective. If there is none, tough luck. We mentioned symmetries yesterday. So this will be a situation where once you branch away one solution, most likely what happens is the algorithm just finds a solution that is structurally equivalent, but different in certain assignments, like think about exchanging the colors in the coloring problem. The objective gains will almost always be 0 in that case. Same for high dual degeneracy, objective gains are 0. So all that is a bummer for pseudo-costs. And even if none of the above applies, there might be situations where you have ties between different variables. So which one do you select then? So I should point out that there are some other local rules which, even those situations, might still work well, pointed back to probing. But I would like to focus on what other useful statistics can we collect about variables. So we collected information about objective changes now. What else is there? So-called inference branching, which again is a history-based rule that keeps track of the average number of bound reductions that you observed from a branching. As mentioned before, so you fix a variable, that fixing might lead to other fixing by domain propagation. You just count how many other fixings did you derive by branching repeatedly on that variable. So this somewhat captures the combinatorial structures. How are variables linked against each other? Which are variables that have a high impact on the remaining problem? It estimates the tightening of the subproblem. So this is all good information. I realize I put an example here. So let's see together whether we understand this. So assume we have this little MIP here, or this little binary program. We fix one variable to 0, so x1 gets fixed to 0. Okay, immediately we see from the first equation that x2 will be equal 1. We get a bound change on the general integer variable, so it was not a binary problem, general integer variable z. So that's 2 inferences that we could get from x1 equals 2. Okay, when we branch on the other side, x1 equals 1, that will fix this variable here. There's no implication from the last constraint, but the second constraint, we are already at 1 less equal 1. So both x3 and x4 have to go to 0 afterwards. We count 3 inferences from that up branch. Again, we can collect those statistics and merge them together to take a branching decision. So this is an idea that's inspired by the constraint programming community, where they don't work with relaxations. They only work with branch and propagate algorithms. And again, you can initialize these values if you don't have statistics in the beginning via probing. Okay, then let's come to VSITs branching. What a name. That's a abbreviation for variable state independent decaying sum. I'm proud that I can remember this. I don't ask you to do so. This has to do with conflict analysis. We will look at this in the second session today, what conflict analysis actually is. For now, just keep in mind, it's a procedure where you learn additional constraints. Whenever you find an infeasible subproblem, you do some deductions that will help you later on to detect infeasibility early. However, this works exactly. This has to do with deriving constraints, and for VSITs branching, you count for each of the variables in how many of these conflict constraints do they appear, and variables that appear in more conflict constraints hence have a better chance of helping you later on in the search to detect something, are better candidates for branching. That's the logic that comes from the SAT community. So solving of logic Boolean satisfiability problems, which is very close to binary programming. And it's, again, a branching rule that might be good also for solving mixed integer programs. And then finally, a very recent development is branching scores based on intersection cuts. It's a lovely theory behind that I won't go into too much detail, but just from the picture here, you see that there's kind of a correspondence between a branching and the cutting plane that you can derive from your branching decision, because it goes to these two intersections here, so-called split cut, which are equivalent to a certain form of Montgomery cuts. And the intuitive idea behind this rule is you consider this distance here, which is, by the way, one of the best measures for classifying cutting planes, as a measure also for branching. Deeper is better. Okay, and that brings you to hybrid branching, which is essentially just taking all of these information, all history statistics that you can get together, and try to merge them into one single score. From an engineering point of view, challenging to get all these different thresholds, all these coefficients, or whatnot, right in the right balance. From a mathematical point of view, trivial at best. So there's other measures that you can throw into the mix, like the number of Kuhn subproblems, the variables, the number of times a variable occurred in an infeasibility proof that you get from the Farkas lemma, and so on. And then, yeah, scale this to a weighted sum, and you might get a very decent branching rule, which is what more or less all the major MIP solvers, to the best of my knowledge, do these days. Instead of taking a weighted sum, another alternative approach is to take something like a leveled filtering. You rank those criteria among each other, and then step by step reduce the candidate set. Start with 1,000 fractional variables, then consider 100, then 20, then 10, whatnot, until you decide on one final candidate. Okay, if you pay close attention, you might have noticed that I always talk about there's one score with which you decide your branching, but all of these statistics exist both for the up and the down direction. How do we combine these things? together. Well, first idea is just take the average. People have been doing this for the first 40-something years of MIP solving software, and then realized, then in between they realized that you might take a convex sum, giving some more emphasis to max or the min, and then after 40 years they realized that multiplying them, taking a geometric mean instead of an arithmetic mean, makes solvers about 10% faster. Fascinating insight message here: a single character code change in your code can make an improvement that today MIP teams dream about. So I was always talking about variable selection, branching on variables. That's what solvers do in 99% of the time. Obviously, you might also branch on different entities, like a so-called general disjunction, which would be a general linear constraint. This is a generalization of variable-based branching, so it obviously has more potential than it. You have more candidates in the mix, so to say. Also, it might be computationally more expensive to select such a branching candidate. There's a couple of drawbacks really with respect to complexity. Statistics might not be as easy to track if you allow a huge variety of different branching candidates. The most important, or one of the most important effects of variable-based branching is that you shrink your problem. You get less and less variables the further you go down the tree. Here you are, in a sense, increasing your problem by adding constraints. So instead of removing variables, adding constraints might make the LPs harder to solve than easier. There's a lot of hand waving in here, admittedly, but there's reasons why this is not working, at least in general, that way. For special kinds of problems and special situations, this might be very decent. Here you have a little impression of why this might be so much more powerful. So consider this funny integer program. Here, if you do variable-based branching, you see there's only one variable that's fractional. So there's only one candidate. You need to branch on that one. Okay, then afterwards, let's take you branch to that direction. Again, you will have a single fractional variable. You need to branch on that one, zag your way up here. I think I once did the counting. It's like 15 or 16 branches until you would find an integer feasible solution. If you just branch on that general disjunction, x1 plus x or minus x2 lesser equal, greater equal, whatever the value is here, you would get there in a single branching step. So it is more powerful. Also, fast forwarding to heuristics, this is also the perfect picture to illustrate why you can't just solve the LP and then round and be happy. Integer solutions might be arbitrarily far away in many different ways of defining far away from the fractional solutions. Okay, one way to make branching on general disjunction work in general, in practice, is branching on so-called multi-aggregated variables. We will see in the pre-solving presentation that in certain situations, the solver will exchange a single variable by such a statement, by like a linear sum. This variable that got exchanged will then not be part of the problem that you're actually solving, because you always replace this with, wherever it appears, you replace this with this linear form here. But the state might still be a good candidate for branching. So in branching on when you branch on multi-aggregated variables, you would, in a sense, pretend that you still had knowledge of that variable and use that form here as a branching candidate, as a general disjunction. Yeah, and that would, in that sense, then represent decisions that you took in the original problem. Okay. After flying through this small quiz, same task, try to think of the answers. Okay, so question number 1, what's the answer? B, yes. Been talking a lot about hybrid bunching for the past 15 minutes, but just strong bunching and pseudo-cost bunching together is what's called reliability bunching, exactly. If you throw other measures in addition, you would get the so-called hybrid bunching rule. Speaking of which, so which of the following measures here are history-based branching scores? A, yes, and B, A and B. Yeah, so resets and inference scores are something that you collect, statistics that you collect over time. Probing is a local information, not a historic one. Okay, finally, last 5 minutes. Node selection gets a little space here. So what are the considerations in node selection? Well, the typical goals are you try to improve the primal bound. You try to select the node in such a way that you would find a feasible solution, because that will help you with the bounding part of the branch and bound process. Also, like in branching, you might try to improve the general global dual bound, like early on in the search space. And I think most importantly, actually, is try to keep the computational effort small when changing from one node to another node. Nodes that are closer to each other are easier to re-optimize. Like a parent node and a child node just differ in one bound change, or maybe plus things that you've propagated. Siblings, the same. If nodes are further away in the tree, there's much bigger difference. So re-optimizing via your primal your dual simplex might take much more time. And also some considerations in the beginning. You might want to create some diversification, in particular when you're applying a parallel variant of a branch and bound algorithm. Okay, and the basic rules for this are depth first search, which is what most of the times MIP solvers do, like 95, 98 of the node selection steps are depth first search steps. And every now and then in between, you will either do like a breadth first search, a best bound, or whatnot. There are different variants. Again, you might combine them by some weighted sum, or doing this one every other time, and every other time you do the other one, different variants. Before closing the session here, or the first presentation, I would like to have a look on what typical branch and bound trees look like. And maybe this is what you have in mind. And this one maybe is actually not such a bad example, because you really see these depth first search step here. So you do a couple of dives after some diversification in the beginning, where you have a full tree here, and then you have a couple of dives afterwards. By the way, these are all taken from actual MIP solver output. These have been generated by Skip. But in reality, things very often also look like this one here. So very degenerated, one huge dive with some offsprings everywhere. Also, this one is not as easy to detect, but it has a very similar shape to the one below, because it's very imbalanced. You're always having in one direction, you have like 95% of the tree. The other direction here, it's just a small tree that repeats pretty much on every level. That's also a very imbalanced tree. Okay, so final quiz on node selection. Okay, let's try to do it together again. What's the answer to the first question? Yeah, most of the times a MIP solver will select as next node either a child or a sibling of the current node, so perform something like a depth first search step. And for question number 2, some split opinions, B. Yes, so with respect to the running time, the node selection empirically has the smaller impact. the branching rule, the variable selection is the more important of the two different choices that you have. So that's it for the first lecture. Thank you.